Somewhere in southern France, there is a bridge that has been carrying water for close to 1900 years, built by engineers who had no lasers, no GPS, and no power tools of any kind. This video works through 4 measured numbers from that structure, the Pont du Gard aqueduct system, and what they actually tell us about the limits of unaided human precision. Before the numbers, it's worth understanding why any of this precision mattered in the first place. A gravity-fed aqueduct has exactly one job: keep the water moving downhill, continuously, across whatever terrain stands between the spring and the city, without ever once letting the channel tilt uphill even briefly. Get the gradient too steep in a given stretch and the water moves fast enough to erode the channel lining and undercut the structure over decades. Get it too shallow, or let it level out even for a short section, and water pools, stagnates, and eventually stops moving entirely. There was no pump waiting to correct a mistake. The gradient had to be right the first time, sustained across tens of kilometers of hills, valleys, and solid rock, and it had to stay right for as long as the structure stood. Start with the whole system. The aqueduct that fed the Roman city of Nimes ran for roughly 50 kilometers from its spring source, winding across the landscape rather than cutting straight lines, because water only flows downhill and every meter of that route had to keep dropping, never rising, all the way to the city. Over that full 50-kilometer run, the total elevation drop was just 17 meters. Do the arithmetic and that works out to an average gradient of about 34 centimeters per kilometer. It's worth being honest here, different sources report slightly different figures for this average, generally somewhere between 24 and 34 centimeters per kilometer, depending on exactly which survey and which endpoints they're measuring from. We're using the most precisely documented version, 17 meters over 50 kilometers, because it's the figure that holds up best under cross-checking. Either way, we're talking about a slope so gentle that standing at one end, you would not be able to see it with your own eyes. That's the average. Now for the extreme. Somewhere along that route, between the Pont du Gard and a town called Saint-Bonnet, Roman surveyors achieved something tighter than the rest of the system needed, a measured tolerance of approximately 7 millimeters of drop for every 100 meters of horizontal distance. That is the steepest precisely measured section on the entire route, and it's a number worth sitting with. 7 millimeters is about the thickness of 2 stacked coins. Spread across a football field's length of ancient stonework, using only sightlines and instruments built from wood and bronze. Now narrow and further, to the single structure most people actually picture when they hear the word aqueduct, the Pont du Gard itself, the 3-tiered stone bridge that still carries the memory of that water channel across the Gardon River Valley. Across its full 456-meter length, the channel drops by only 2.5 centimeters. Convert that into a ratio and you get a gradient of roughly 1 in 18,241. And that line has held, not approximately, not roughly, but essentially unchanged, for approximately 1900 years, through earthquakes, floods, and the ordinary settling of stone under its own weight. So how did they actually do it? Not with anything you'd recognize from a modern surveying kit. The primary instrument was the groma, a simple wooden cross mounted on a vertical staff, with plumb lines hanging from each of its 4 arms, used to sight straight lines and right angles by eye. For measuring elevation and slope specifically, engineers used a dioptra, or in some contexts a related water level instrument called a chorobates, a long wooden trough or straightedge, leveled using either a water channel cut into its surface or hanging plumb bobs, then sighted along like a rifle scope with nothing but the human eye at both ends. No lenses. No electronics. No lasers bouncing off a reflector half a kilometer away. Just line-of-sight sighting instruments, patient remeasurement, and an engineering culture that treated a few millimeters of error over 100 meters as something worth correcting rather than accepting. For comparison, a modern rotating laser level, the kind used on ordinary construction sites today, typically holds an accuracy of around 3 millimeters over 30 meters, and that's an electronic instrument correcting itself dozens of times a second. The Roman surveyors on the tightest section of this aqueduct were working, by hand, with wood and bronze and their own eyesight, within roughly the same order of magnitude, sustained not over 30 meters but over 100, and not for one afternoon of measurement but for a structure meant to outlast its builders by millennia. They didn't have a way to double-check their work against a satellite. They had string, plumb bobs, patience, and the willingness to remeasure a stretch of ground as many times as it took before committing stone to it. 34 centimeters per kilometer, on average. 7 millimeters per 100 meters, at the tightest point ever measured. 2.5 centimeters of drop across the bridge itself, holding for 19 centuries. And all of it achieved with a chroma and a dioptra. No figure in this video is invented. Where the sources disagree, on the average gradient specifically, we told you so instead of picking whichever number sounded most impressive.